Okay, let us see how do you plot the root locus for this open loop transfer function. So here we are considering the feedback is negative and h of s is 1. So this is the open loop transfer function of a certain system. So looking at that, we can locate the open loop poles, so which are at origin, and it's at okay, let me just write it as, so one more is at minus 4, and there are two complex poles having its real part at minus 2 and its imaginary part is plus j2, and we have it one at minus j2. So this is the 4 pole positions. Now as you know that we need to first identify, this is my S plane. So in the S plane, on the real axis, which part of the real axis is a part of root locus? So now, as you know, okay, this is not a part of root locus because there is nothing to the right of this. So if you come in this section, you stand anywhere to the right of it, either you will see one pole or three poles. Okay, 1, 2, 3, or suppose if you stand here and then look towards the right, you have 1. If you stand here, look towards the right, you have 3. So when you have complex poles, so complex poles will not alter that number of poles looking into the right of that particular section. So in this segment, if you look towards the right, you have odd number of poles plus 0, so a root locus exists here. So now it is actually living in this, living from the origin and living from minus 4. That's why the arrow mark is living here and it's living here. So, and of course we need to find a breakaway point. Breakaway point need to be found. So we have to find the asymptote specifications. Asymptotes, about asymptotes we need to find out, which is how many asymptotes, what is centroid, what is the angle of asymptotes. Those things we shall list it now. The loci will start from the open loop pole positions, and if you look at the asymptote, okay, number is p minus z, the number of asymptotes are 4. So naturally the angles will be, so 45 degrees one of them, 135 is the other one is 225 degrees, and next is 315 degrees. So these are the 4 asymptotes which will be lying at a centroid. Centroid is given by summation of all pole positions, that is one is at origin, other is at minus 4, and one more is at minus 2, and its real part is minus 2. Of course we don't have any zeros here, divided by 4. So it's actually minus 8 by 4, which happens to be minus 2. So there is a centroid. I can write a centroid at minus 2 at an angle of 45 degree. This is 45 degree. This is 135. And this is 215. This is 225 and 315 degrees. So these are the 4 asymptotes which are centered at minus 2 as a centroid, and the angles are 45 degree, this is 135, this is 225, this is 315. Next I need to find what is the breakaway point. To find breakaway point, we know that I need to do dk by ds equal to 0. So to do this, first I should find what is k value. To know the k value, let me first find out what is del of s. So del of s is nothing but again it is 1 plus g of s into h of s equal to 0. You can get it this from, this is 1 plus, what is g of s into h of s? It is k by s into s plus 4, s plus 2 plus or minus j2. So which, of course this is equal to 0. So then this comes out to be s into s plus 4, s plus 2 plus or minus j2 plus k equal to 0. Of course in the denominator you have this, if that is equal to 0, that denominator will go off. Now this can be reduced to s square plus 4s and this will be s square plus 4s plus square of this plus square of this, so which will be 8. The way how this will come is, so you can write it as s square plus twice of this as the quotient of s 4s, and the s power 0 quotient will be square of this plus square of this. So square of 2 is 4 and square of this 2 is again 4, this is 8. So this is how do we get it. So this is s square plus 4s plus 8 is this value, and of course plus k equal to 0. So I have done this here, so you can just have a look at it. So I just multiplied this, so s square this, so I will end up with this as my term. So let me just write this. Okay, we'll write the roots or all those things later. So this will result in, maybe you can just pause for some time and then get the expression s power 4 plus 8s cube plus 24s square plus 32s plus k equal to 0 is my characteristic equation. So s power 4, 8s cube, 24s square plus 32s plus k equal to 0 is my characteristic equation. So let us differentiate this, try to get the roots. So dk by ds equal to 0 will result in, so now it is 4s cube plus, this is a differentiation of this equation, so it is 24s square plus 48s plus 32 equal to 0 is my dk by ds. So let us find the roots of this. If I try to find the roots of this, which can be easily found using the calc, because this is order 3, so I will select equation, next order is degrees 3, so quotient of s cube is 4 and this is 24 and this is 48 and the other one is 32. You have minus 2 as one of the root, and then it's again coming as a. Suppose if you find the root, it's minus 2. So when you press it again, you would have got actually the other root. So the thing here is for this particular cubic equation, the roots are minus 2, minus 2, minus 2. There are actually 3 roots repeating at minus 2. The roots of this is actually s plus 2, s plus 2, s plus 2. The roots are minus 2, minus 2, minus 2. So that's why we are getting it like this. You can see, if you ask for this x is equal to minus 2. The next one is, it is not showing because it's a repeating. So this is my breakaway point. So BAP is minus 2, minus 2, minus 2. Now the question is, what does this minus 2, minus 2, minus 2 breakaway point means for this root locus, because I know that this has to come like this has to come like this, they have to break here. So once it is breaking here, then why the 2 more breakaway points at minus 2, minus 2? So there are actually all the 3 are valid. So one is happening at minus 2 because of these 2. Let us see how do we validate the other 2 breakaway points which is there existing in the desired region of my root locus of my real axis. So now before that, shall we find what is the angle of departure of this? So angle of departure of this is, so we know that theta d is known by 180 degree plus phi. So this phi is actually summation of theta 0 minus summation of theta poles. So I don't have any zeros, it is 0 minus summation of theta p is actually I have 1, 2, 3 poles. So it is theta p1 plus theta p2 plus theta p3. So let me approximately draw the lines here. So this is the line joining this. This is joining this pole to this and this to this. So So let me say this as theta P1, theta P2, and this is theta P3. So these are the three poles which are joining to this one. So to find what is theta P1 is actually whole 180 degree minus this angle. So it is 180 degree minus tan inverse of course, for this angle the height is the opposite is this, which is 2, the adjacent is 2, so it is tan inverse of 2 by 2, which will be 45 degree. So it is 180 minus 45 degree, which is 135. So I'll just do this mode 1. It is 180 minus 45 is 135 degree. It is 135 degree is theta P1. So what is theta P2? Just a minute. So this is how I got theta P1 is 180 degree minus tan inverse of 2 by 2. This is 135 degree. Theta P2 is actually this angle. Theta P2 is this angle, which happens to be 90 degree. You can see it is just above that one. It is 90 degree. What is theta P3? Theta P3 is actually this angle, the angle that is subtended by this. So it is tan inverse of opposite by adjacent. Opposite is of height 2. The adjacent side dimension is, this is minus 4 minus 2. The separation is again 2. So it is tan inverse of 2 by 2, which is again 45 degree. 45 degree. So what is summation theta P now? It is theta P1 plus theta P2 plus theta P3, which happens to be 135 degree plus 90 degree plus 45 degree. So now if you sum it up, this will be 270 degree, correct? So this is 135, this is also 135, it is 270 degree. So now it is, I can write theta D is equal to 180 degree plus 0 minus, this is 270 degree, which happens to be minus 90 degree. So this is theta D for this particular pole, meaning this open loop pole which is there at this point, as the value of k increases, becomes the closed loop pole, will leave at an angle of minus 90 degrees, actually this angle. So this is minus 90 degree, it is coming like this, and since it is minus 90 degree for this, so there will be a mirror image which will be plus 90 degree for this. So this is the angle of departure of this closed loop pole. As k increases, it's departing like this. So we know that these two poles started from 0 and minus 4. They are actually going like this, and they break here. Once they break, they will become complex. If you can see this is coming from minus 2 plus j2, and this is going from minus 2 minus j2. Actually this is coming down, this is going up at the same real axis of minus 2, at the real axis value of minus 2. So what happens is, this is coming here and this is breaking here. Once it breaks, you actually have 2 here. So this is coming like this, and this tries to go up like this, but by that time this also has reached here. So we saw that there was a breaker point minus 2. So that minus 2 breaker point was valid for these two poles which were coming in opposite direction. They broke here, and one tries to go up and other tries to go down. The one which is trying to go up will again break with this one which is coming down, and one will go like this, other will go like this. Let me clarify. The two poles, of course we will see the simulation once and you can clearly get it. The pole is coming in the two poles are coming in opposite direction. They will break here. One tries to go down and one will go up. The one which is trying to go up will again collide with this closed loop pole which is already there at this point at minus 2 itself. So once they break, they are actually going like this, because there is asymptote at 45 degree 135, and the one which is trying to come down here will again collide with the one which is going up here. So they will again break at minus 2 here, and it will break at minus 2, it will go in the direction of the asymptote. So minus 2, minus 2, minus 2, whatever we had. So there are 3 breakaway points, one corresponding to the opposite one, that is from 0 and minus 4, and the other one is from this complex pole which is coming down, and to the one of the one which is broken here, and the other one which is broken here is coming down. But by that time this has reached minus 2, it will again break. So ultimately they go and cross the imaged axis at some point. So we can actually find what is the point of intersection of this at the imaged axis. So that can be found by writing the Roth's array. So before writing the Roth's array, I have the characteristic equation here. So let us write this characteristic equation, write the Roth's array. So what this characteristic equation is? Okay, maybe for this characteristic equation I can write the Roth's array. So what is the first question? This is s power 4. Is it not 1, 24 and k? This is s cube. Is it not 8, 32, 0? So now let us write s square. Is it not 8 into 24 minus 32 by 8? Is it not 8 into k, 8k minus 0 by 8? So is it not k, then 0? Then what is s power 1? So what is this? So this is actually 8 into 24 minus 32 by 8. It's actually 20. So this will become 20. So now it is 20 into 32 minus 8k by 20 and 0, 0, and s power 0 will become k 0, 0, because this into this minus this into this by this, so which happens to be k. So I am just repeating, sorry for that. So this last element is whatever value that you get here multiplied by k minus this into 0 is that 0 divided by this is, you'll end up with k here. So now because there are already 2 zeros in this row, if this 20 into 32 minus 8k by 20, when it becomes 0, then the k value is k margin. K value is k margin. So by using this I can find the k margin. So what is k margin now? So it is 20 into 32 minus 8k is equal to 0. Therefore k is equal to 20 into 32 by 8, which happens to be 20 into 32 by 8 is 80. You have the value of k margin, which is 80. So this is k margin. So when k margin is 80, so do we know what is del of s? Sorry, a of s, auxiliary equation. I can find auxiliary equation, which is nothing but, so this is 20s square plus k margin is my auxiliary equation, correct? Equal to 0 is my auxiliary equation. So from which I can write what is a square is equal to minus 80 by 20. This will go off and this is 4. Is this a square is equal to plus or minus j2, because square root of 4 is 2. So you have, sorry, this is this. So the roots of this is, the roots of this is plus or minus j2. So meaning it will cross imagined axis at j2 and this will cross at minus j2, minus j2. So what is the system stability? System is conditionally stable for values of k. If the value of k is more than 80, system is unstable because two roots go to right side. If the value of k is less than 80, then system is stable. System is stable. So for values of k between 0 and 80, system is stable. System is stable. Let me show you this in 20 sim. So this 20 sim is another tool where you can able to visualize the pole zero motion. So this is 20 sim. This is a freely downloadable tool. So once you install this, click on this insert, go to submodel. In that submodel, go for linear systems. So in this linear system, you can edit the transfer function in many ways, either in transfer function or pole zero gain or eigenvalues or state space. So let us use this pole zero and gain to edit the to enter our transfer function. Our poles are at, you can see this is my pole position. These are open loop pole position. One is at 0, other is at -4, and 2 more at -2 plus or minus J2. So let me do that. Let me add, okay, there is a pole, this is a pole I am editing, so there is a pole at, okay, let me just see both of them simultaneously. So see, now I have pole at 0 and I'll add another, so there is a pole at -4, let me edit -4 here. So this I applied, so this is at 0, this is at origin, this is at -4, and I have, okay, this is -2, this is plus or minus J2. Can you see this is -2 real axis, real value, and imaginary is plus or minus 2. Okay, this is applied. So we have, okay, what is that? Let me, that -4 is missing. Okay, no, because I didn't apply. See, now I have one pole at origin, two are complex, and one more at -4. So we have applied this. Then you say okay. Then you plot pole zero plot. Oh, this is what you have. See now. So this is what we expected. Can you see? This is what is expected. The pole is coming down here. This is going up here. This is going on left side, sorry, right, and this is going to left. They are breaking at -2, and they are ultimately going, which you can see exactly the same way how you're expected. So let us see how this happens. So there is an option that you can actually change the value of k now. So now see, this is the value of k. So value of k is, you can see, it is 0. System linear system k is 0. When it is 0, you can see this is my pole, and the pole is, one more pole is here, the other pole is here, other pole is here. The moment you start increasing the value of k, see here, there's all the, you can see the value of k is increasing. You can see I'm increasing the value of k. See that? Can you see the poles? This pole has come from here to here, whereas this has come from here to here, this has come from here to here, this has come from here to here. So for a k value of, what is the value of k? You can see the value of k is 12. So when 12.5 is the value of k, all the poles have left the open loop pole position. If I further increase, you can see the poles are coming here, the poles are coming here, the poles are coming here. For a certain value of k, they will meet at -2. Can you see they are meeting at -2? So they are all, now this is the point. You can see it's almost at -2, -2, all of them. So now they will break. Maybe what you can do is you can just zoom this portion. You can zoom this portion. Now if you further increase, actually what happens is, so now this is at -2, they will break here. So this is not properly seen there. Actually it will come here, it will break there. So what I can do is, because when we actually solve the breaker point, so all the breaker points are at -2, -2, -2. That's what is our theoretical thing. Maybe here we are not seeing that they're all meeting at -2. So it's exactly happening at -2, -2, -2. You can see once they break, can you see they are moving out like this? Where they are going? They are all going to infinity. So if you just come back here, so they break here, and then this is for a lesser value of k. As the value of k is less and less, so they're you can see they are coming here. they break at this point and then they are going like this. Actually the breaker point minus 2 minus 2 minus 2, what you got, meaning that all the poles will, okay, 2 will break here and other one which is going up will going to again break with this, and they are actually going, one asymptote is taken care by, or one loci is taken care by this asymptote which is lying at 45 degree, this is at 135, this is at 225, this is at 315. So this way we can able to see how the, of course this is a good visualization, okay, how the poles will come, they'll meet here and they again break, they'll again break. Of course when you zoom this portion, so this is coming out to be like this, but to be very frank, so we don't have, of course we have one of the breakup point which is minus 2 and others are also at minus 2 minus 2. Okay, this is how we are having the breaker points, and this will actually not exactly the same, so they will actually come here and break at this point and they again break here, they again break here, and ultimately it will look like this, it will look like this. So that is one small, okay, maybe you can just try the same thing in MATLAB also. What I can do is I can go here to MATLAB. So let us find this. I can edit the roots. Give me a minute. Okay. What are, okay, let me, because I know the transfer function, I can edit it. Maybe this one. This is, let's say 0. That is 1 over s, and this is 1 over s plus 4, and the other one is 1 over s square plus 4s plus 8. This is 4s plus 8. Okay, with this I'm done. Okay, let us see what happens. What is this expression it is saying? Oh, this one, sorry. Okay, let me get that. This is what I have, exactly this one here. See now, this is the breaker point. So the breaker point, the poles will break here, and so because one is coming at plus 90 degree, other is coming at minus 90 degree, they break here and all of them are breaking at minus 2 minus 2 minus 2. So if you zoom it out, you can able to so this is how the loci will move. You can, I think you can able to find the K margin somewhere here. Can you see this is 70.6, which is still there to the left, poles are still there to the left. Let me just zoom it and try to find out, can I able to find, because K margin here from theoretically it is 80. If I can able to place the node, it's fine. Let me just find the node point. No, I am unable to come here. Can you see it's 84.3? Shall we see here? Can I able to locate that? Okay, I will increase this K value. No, it is, next point is going to right and it's there to the left. You can see now it is less than 36. When it comes here, it's more than 80. You can see it's 140. So this is better here. Okay, this way we can able to visualize the poles which are moving like this. Now what you can do is, okay, as I already shared the material, you can slightly make this pole to come down here. So let the real axis be there at let the complex pole real part be -2. Let us make the imaginary value as, instead of -2, let us make it as. So this is the small change I am making here. Let me just have a look at it. I'll show you this. So let us make this as -1. The moment I make this -1, so this will become s square plus 4s plus, this will become 4, 2 square is 4 and 1 square is 1, so it will be fine. If I edit this, let us see what happens. So the breakaway points will be, one will be -2, other will be here, other will be here. So that you can refer to my material which I have shared. Though one of the breakout point is -2, the other one will be here, the second one will be here. So let me just edit that value both in 20 sim and this. So let me go to 20 sim and then edit this. So in this edition it is not plus or minus 2, let me make it plus or minus 1. If I apply, say OK, see the pole 0, see now, if you see this, if you actually increase the value of k now, can you see the poles come here? The one of the breaker point is -2, so first they will break, so it will break there. By that time these two are still very close to the open loop pole position. If you further increase the value, can you see the one which is broken at -2, they are coming now here and they break with the other one which is coming in the opposite direction. They break here and then they go like this, meaning if I just write it over here, that is, so this is my, one of the pole is at origin, other one is at -4. The other complex poles are having real part as -2, but the imaginary is plus j1, this is minus j1. So now what happens? Of course, angle of departure, if you find out this is -90 degree, that will be plus 90 degree. So what happens here is, this will go like this, this will go like this, and this is coming down here, this is going up here, this is going up here. They first break and they go here, because I know that there is a asymptote at centroid -2, this is this, this is this, this is this. So now once they break, it's going in this opposite direction. They again break here, one will go here, other will go here, they will again break here, this will go here, this will go here. So this is how it happens. So that's what you are seeing over here. See here, let me just track the value. See now, as the value of k increases, this is coming, so it breaks first at -2, this is -2. If I further increase, they are again breaking here, so they are breaking, you can see now they break and then they go like this. So you can see the same thing in your MATLAB also. So then this will be not 8, but it will be 5. If I make it 5 and if I run it here, see that, if you just open it, just see, this is coming down, going up, so it breaks here and then it's going here, it again break, and this is taken care by these two asymptote, and these two are, again you can see it's ultimately going to infinity. And of course system is conditionally stable, you can actually find the value of k at which this happens. In the next category, in the same category, so instead of making it as -1, let us make it as -3 as your imaginary part. So meaning I have a transfer function which is s into s plus 4, this is s plus 2 plus or minus j3, plus or minus j3. So now what you have is, this is my pole, this is my other pole, this is minus 2. Instead of having it at minus 2, I will put it at plus J3 and minus J3. It is a bit above. Now what happens is, this is a part of root locus, this is a part of root locus, it goes here, it goes here. First it will break. If you still find the angle of departure is minus 90 degree for this, so this will be plus 90. So this is coming up here, this is going down. The moment they break at minus 2, one tries to go down, other tries to go up. The one which is going up, the one which is going down will again break somewhere here, and one will go here, other will go here. Here we know that one is coming down, other one is going up, so they break somewhere here, they go like this. So this is how now the breaker points is complex. One is minus 2, other two will be minus 2 plus or minus some jx. So that x is between, maybe it is halfway somewhere here. So that you can find out using dk by ds. So now this is the special to special case where you have a breaker point which is complex in nature, So now let me edit that here and then try to see it. Okay, let me just take out that, let me edit. So what is the addition now? So now this will be, instead of 1, that will be 3. Apply, say OK, then pole 0, see now? Now let me increase the value, okay, as you are there at origin, 0, the poles are leaving from open loop poles. Just have the dot, have a look at the dot and that arrow. Can you see Aarti now first coming? So does these two dots meet first? Minus 2 is first breaker point. Can you see now it's going up now, So can you see now it's breaking with this. Now once they break, are they departing? Where they are going? So they are going guided by the asymptotes, at 45 degree, 135. That's what is we have seen. So of course we have asymptotes here. So we have asymptotes which are there and this. So they are being taken care of. Same thing can be visualized in your MATLAB also, where you have to change this to. So that will be now a square plus, that is 9 plus 4 is 13. If I make it 13, you can see how we get it. See that? This is, one is minus 2, other two are complex. So this way you can able to visualize different types of system. Of course, all the three systems are condition stable. Of course, that condition of k margins keep changing from example to example. Okay, thank you.